Good morning, champ. Up to now, our fluids have lived in a perfect world. No friction, no fittings, just smooth streamlines and ideal energy exchange. But in the real world, every pipe has rough walls, valves, elbows, and expansions that quietly drain energy away as heat and turbulence. Today, we're upgrading Bernoulli to handle reality. We'll add head loss, include both friction and fittings, and learn to see energy flow using the energy grade line and the hydraulic grade line. By the end, you'll read a pipeline like an engineer, seeing exactly where energy is stored, lost, and how to quantify it. We've been using Bernoulli in this familiar form. Pressure plus 1/2 times density times velocity squared plus density times g times z equals a constant. That's perfect when analyzing forces or momentum, but when we want to plot how energy changes along a pipeline, it's more convenient to express it per unit weight. So the vertical distances on a diagram literally correspond to head. Dividing through by density, G gives pressure over density G plus velocity squared over 2G plus Z equals a constant. We presented it before in the volumetric form, but this head form is handier for visualizing the energy grade line and the hydraulic grade line, which we'll use throughout this episode. In a real pipe, energy isn't perfectly conserved. As fluid flows, it rubs against the pipe wall. That's friction, and collides with fittings like elbows, valves, and expansions. Each of these effects dissipates mechanical energy as heat or small-scale turbulence. We combine them into one term, the total head loss, H sub L. So the real Bernoulli equation between 2 points becomes pressure 1 over density G plus velocity 1 squared over 2G plus Z1 equals pressure. 2 over density G plus velocity 2 squared over 2G plus Z2 plus H sub L. That final term represents all energy losses per unit weight between points 1 and 2. The total head loss splits into two parts, major losses and minor losses. Major losses come from wall friction along the straight parts of the pipe. Minor losses come from fittings, valves, bends, and expansions. Each minor loss is written as H sub m equals k times velocity squared over 2g, where k is a dimensionless coefficient found from experiments. For the frictional part, engineers use the Darcy-Weisbach equation. H sub f equals f times L over d times velocity squared over 2g, where f is the friction factor, L the pipe length, d the diameter, and v the mean velocity. The friction factor depends on the Reynolds number and the pipe roughness. That's what we'll study next time. So our complete real-world Bernoulli equation becomes pressure 1 over density G plus velocity 1 squared over 2, G plus Z 1 equals pressure 2 over density, G plus velocity 2 squared over 2G plus Z 2 plus F times L over D times velocity squared over 2G plus the sum of K times velocity squared over 2G for every fitting. Now let's actually visualize these energy terms. The energy grade line represents total energy per unit weight. It includes pressure head, velocity head, and elevation. The hydraulic grade line represents pressure and elevation only. The hydraulic grade line always sits one velocity head below the energy grade line. Now, let's apply it to a practical example, a horizontal pipeline with fittings. We have a steady flow through a pipe of length L and diameter D, with one elbow, one valve, and one sudden expansion. To simplify analysis, we'll assume the mean velocity is roughly constant. Velocity 1 equals velocity 2 equals V. Why is that okay? Because the pressure taps are placed in equal diameter straight runs far from the fittings, where the velocity profile is fully recovered. The flow rate is steady and incompressible. So with equal cross sections at both taps, continuity guarantees the same average speed. Local accelerations and separations inside the fittings are captured by the K-loss terms, not as changes in section velocity. With that assumption, the Bernoulli equation simplifies beautifully. Pressure 1 plus 1 half density V squared equals pressure 2 plus 1 half density V squared plus density G times H sub L. The kinetic terms cancel, leaving pressure 1 minus pressure 2 equals density GH sub L. The total head loss is the sum of the friction loss and the minor losses. H sub L equals F times L over D times velocity squared over 2g plus the sum of k times velocity squared over 2g for each fitting. Substitute this back in and the pressure drop becomes delta P equals 1/2 density V squared times the quantity FL over D plus the sum of k values. That's the full picture. Friction plus fittings. The complete real-world pressure drop. On a diagram, you'd see a pipe with 3 fittings, an elbow, a valve, and an expansion, and above it, the energy grade line sloping down with little steps at each fitting. Those steps are the energy losses, both major and minor. And that's how engineers calculate the pressure difference between 2 points in a real pipe. The smoother the walls, the shorter the pipe, and the fewer the fittings, the flatter that line becomes. So champ, this is Bernoulli meeting the real world. We started with a perfect equation, added one new term, and suddenly it models real pipelines, pumps, and networks. Friction, valves, bends, they all take a share of the energy. And with the energy grade line and hydraulic grade line, you can literally see where it goes. Next time, we'll discover where that friction factor really comes from. Laminar versus turbulent flow, and the mighty Reynolds number that decides it all. Keep your flow steady, your equations balanced, and your energy line gently sloping.